In 1977, a radio telescope in Ohio detected a signal from deep space, unlike anything astronomers had ever seen. It lasted exactly 72 seconds. The scientist reviewing the data stared at the printout, circled the signal, and wrote a single word beside it. Oh, wow. No one has ever detected it again. It remains one of astronomy's most enduring mysteries. But it is far from the only one. Deep in the universe lies a region so vast and so empty that it stretches across 330 million light years, containing far less matter than our best models say should be possible. A distant star fades by nearly a quarter of its brightness, with no predictable pattern, and after years of observation, no single explanation has accounted for everything astronomers have measured. The James Webb Space Telescope has revealed galaxies so massive and so fully formed that they appear to have existed far earlier than current theories of cosmic evolution allow. Meanwhile, the universe itself is expanding, but every precise method scientists use to measure that expansion arrives at a different answer. Both methods have been tested repeatedly, both appear to work, yet they cannot both be correct. And somewhere between the stars are planets with no sun at all, wandering through permanent darkness, carrying mysteries of their own. None of these discoveries was the goal. Scientists were searching for something else entirely. Instead, they uncovered evidence that the universe may be stranger than our best theories can currently explain. This channel grows because of people who take a moment to like and subscribe. If you're one of them, thank you. It means we get to keep doing this. Let's start with the 72-second signal that has puzzled astronomers for nearly half a century. Before we can understand any strange discovery, we need to consider the way we actually observe the universe. When you look into the night sky, your eyes collect only visible light, a remarkably small slice of the enormous range of energy traveling through space. Stars, galaxies, and clouds of gas are constantly sending out many other forms of light that our vision can never detect, leaving much of the cosmos hidden unless we build instruments capable of revealing it. Radio waves uncover enormous clouds of cold hydrogen stretching between galaxies. X-rays expose regions where matter has been heated to extraordinary temperatures around black holes and exploding stars. Gamma rays reveal the highest energy events ever witnessed, including violent bursts that race across billions of light years before reaching Earth. Each observatory listens to a different part of nature's broadcast, and each uncovers details the others cannot provide. Together they assemble a far richer portrait than visible light alone could ever offer. Among the newest of these instruments is the James Webb Space Telescope. Unlike the Hubble Space Telescope, which primarily observes visible and ultraviolet light, it was designed to study infrared light, a longer wavelength that easily passes through cosmic dust. That ability allows us to peer inside stellar nurseries where new stars are forming, and to glimpse galaxies whose visible light has been stretched into infrared by the expansion of the universe. Almost immediately after beginning scientific operations, it revealed ancient galaxies appearing larger, brighter, and more mature than many researchers expected. Distance itself also transforms every observation into a journey through history. Light travels at a finite speed, although unimaginably fast. Whenever you see an object 1 billion light years away, the light entering the telescope began its voyage 1 billion years ago. The galaxy may have changed completely since then, yet we can observe only the version whose ancient light is arriving today. Looking farther into space, therefore, means looking farther into the past, allowing astronomy to become a form of cosmic archaeology. Every image, spectrum, and measurement throughout this journey rests upon methods tested repeatedly by independent researchers around the world. Observations are compared, challenged, refined, and published before becoming part of our understanding. Some interpretations continue to evolve, yet the underlying discoveries remain grounded in careful evidence gathered across many instruments and many years. That foundation matters because the universe never arranged itself to match our expectations. These structures, signals, and forces existed long before anyone pointed a telescope toward them. We did not invent their behavior, and we cannot negotiate with the evidence they leave behind. We simply continue building better ways to perceive what was always there, gradually extending human vision beyond the narrow band of light nature granted our eyes, one remarkable discovery after another. Imagine plotting every major galaxy across an enormous region of the universe, expecting countless islands of stars woven into the familiar cosmic network. Then, instead, you encounter a vast expanse where those galaxies are strangely scarce. That unexpected absence is known as the Boötes supervoid, a region in the direction of the constellation Boötes, lying roughly 700 million light years from Earth. It is remarkable for what it does not contain. The supervoid stretches across approximately 330 million light years, making it one of the largest known structures in the observable universe. Within that immense volume, astronomers find roughly 60% fewer galaxies than standard cosmological predictions suggest should exist. Space there is not completely empty. A few galaxies remain scattered throughout, yet compared with neighboring regions, the difference is unmistakable, as though an enormous section of the cosmic web failed to develop as expected. Modern cosmology predicts that gravity gradually gathers matter into filaments and clusters while leaving expanding gaps between them. Those gaps are called voids, and they are a normal feature of the universe. The Boötes supervoid, however, occupies the extreme edge of what current statistical models comfortably produce. Researchers can simulate countless universes on powerful computers, yet creating a void of this scale remains exceptionally uncommon under the accepted picture of cosmic evolution. Another layer of the mystery emerged when astronomers compared its location with the cosmic microwave background, the faint microwave glow left behind after the Big Bang. This ancient radiation covers the entire sky and preserves tiny temperature differences from the universe's earliest history. In the direction of the Boötes supervoid appears an unusually cold region, commonly called the cold spot. The alignment between these two features has inspired years of careful investigation. One possible explanation suggests that light traveling across such an enormous underdense region gradually loses slightly more energy than expected before reaching us, creating part of the observed temperature difference. Calculations indicate this effect may contribute, although many studies conclude it cannot fully explain the cold spot by itself. The puzzle therefore remains open, encouraging researchers to explore additional possibilities while testing each idea against observation. Among the more speculative proposals is the suggestion that the cold spot records the ancient imprint of a collision between our universe and another during the earliest moments of cosmic history, before the rapid expansion known as inflation reached completion. This concept arises within certain multiverse models and has been explored mathematically, yet no observation has confirmed that such an event truly occurred. It remains an intriguing hypothesis rather than an accepted conclusion. As we consider the Buddhist supervoid, the discovery invites restraint as much as imagination. The evidence clearly establishes an extraordinary region of space, while its deeper origin continues to resist complete explanation. Sometimes the most revealing discoveries are not brilliant objects blazing across the cosmos, but immense absences that remind us our maps of the universe still contain places where established theory and observation have yet to meet completely. A massive star can spend millions of years resisting gravity. When its fuel finally fails, that balance disappears within moments. The core collapses so violently that protons and electrons are crushed together, leaving an object composed largely of neutrons. In rare cases, the remnant emerges with something even more extreme, a magnetic field, unlike anything else known in nature. We call such an object a magnetar. It is a specialized neutron star whose magnetic field can reach roughly 1,000 times the strength of an ordinary neutron star. Matter there has already been compressed beyond familiar experience. A teaspoon of neutron star material would have a mass approaching 1 billion tons under Earth gravity. Yet, density is only part of what makes a magnetar extraordinary. Its magnetic field dominates the surrounding environment. Close enough, ordinary atoms would be severely distorted as electrons respond to forces vastly stronger than anything naturally encountered on Earth. At a hypothetical distance around 120,000 miles, halfway between Earth and the Moon, a magnetar's field could disrupt magnetic technology across our planet. Living tissue would face effects far beyond conditions biology evolved to survive. We have already measured that influence across interstellar distances. On December 27, 2004, instruments orbiting Earth registered an enormous flash from soft gamma repeater 180-6-20. The magnetar lies roughly 50,000 light-years away, on the opposite side of much of the Milky Way. Its eruption lasted only about 0.2 of a second during its brightest initial spike. Within that fraction of time, the event released more energy than the Sun produces over roughly 250,000 years. The radiation crossed 50,000 years of space before reaching our planet. Even after traveling that distance, it measurably disturbed Earth's ionosphere, the electrically charged region of the upper atmosphere. The source itself had barely changed size. Magnetars are only about the dimensions of a city, yet their crusts endure immense stresses as the magnetic field evolves. When that crust shifts or fractures, magnetic energy can be released abruptly. The resulting eruptions range from smaller bursts to giant flares like the event observed in 2004. Only a few dozen magnetars have been firmly identified in the Milky Way and nearby satellite galaxies. Their active lives are relatively brief on astronomical timescales, which makes the surviving population difficult to count. Estimates of dormant or difficult to detect neutron stars with magnetar strength fields remain highly uncertain. That uncertainty matters. Magnetars demonstrate how an object can be physically small while controlling an environment extending far beyond its surface. From Earth, we encounter them only through radiation arriving across immense distances. Yet even here, protected by tens of thousands of light years, our instruments can record the moment when a dead stellar core rearranges its magnetic field and sends the consequence outward through the galaxy. Some discoveries begin with a brand new observation. Others spend years hidden inside data that nobody realized was extraordinary. Fast radio bursts entered astronomy in exactly that way. In 2007, researchers examining archived recordings from the Parkes Observatory in Australia uncovered a brilliant pulse of radio energy. The signal itself had actually reached Earth in 2001, remaining unnoticed for 6 years, until someone looked back with fresh questions. The burst lasted only a tiny fraction of a second. Most fast radio bursts endure somewhere between a fraction of a millisecond and only a few milliseconds before disappearing completely. During that astonishingly brief interval, a single burst can release as much energy as our sun emits across 3 full days. By the time the signal reaches our telescopes, it appears as nothing more than a brief spike on a computer display. Yet, its journey may have begun billions of light years away. Those enormous distances add another remarkable detail. As radio waves travel through intergalactic space, they pass through thin clouds of charged particles that slightly delay different frequencies. Astronomers measure this effect, called dispersion, to estimate how much material the signal crossed before arriving. The result consistently points toward sources far beyond our own galaxy, making fast radio bursts among the most distant transient events ever detected. At first, many researchers imagined a single catastrophic event. A collapsing star or a violent collision seemed capable of producing one brilliant flash before vanishing forever. That explanation weakened dramatically when certain bursts repeated. One source, formally designated Fast Radio Burst 201-21102 alpha, has produced hundreds of detected pulses over many years. Whatever powers it survives each eruption, eliminating theories that depend upon a one-time cosmic destruction. Progress accelerated in 2020. Astronomers detected a fast radio burst originating inside the Milky Way and traced it to a known magnetar named soft gamma repeater 1935 plus 2154. For the first time, one source had been identified directly rather than inferred from distant observations. The discovery strongly supported the idea that at least some fast radio bursts are created when magnetars undergo sudden magnetic upheavals, capable of releasing enormous bursts of radio energy. Even so, the mystery remains larger than a single explanation. Many bursts differ in brightness, repetition, surrounding environment, and detailed structure. Some arrive with extraordinary precision, while others appear isolated and never return. The search for extraterrestrial intelligence community has therefore never completely ruled out an artificial origin for certain unusual events, although the overwhelming scientific consensus continues to favor natural astrophysical processes based on the available evidence. By 2024, astronomers had cataloged more than 600 fast radio bursts. Most still have no confirmed source. Each new detection adds another carefully measured clue, reminding us that even across billions of light years, the universe can announce its presence in the briefest imaginable whisper of radio light. Most astronomical discoveries begin by finding something unexpectedly bright. This one began because a perfectly ordinary star kept fading in a way that made no sense. Hidden among the observations collected by the Kepler Space Telescope, a point of light in the constellation Cygnus repeatedly behaved unlike any other known star. Its formal designation is Kepler 8462-852, though it became widely known by a far simpler name, Tabby's star. The discovery arrived in 2015 through the efforts of citizen scientists participating in the Planet Hunters project. Thousands of volunteers examined Kepler observations by eye, searching for tiny changes in starlight that computer algorithms might overlook. Among those volunteers, several noticed a pattern so unusual that professional astronomers quickly began investigating it in detail. Normally, when a planet crosses in front of its star, the brightness drops by a small, predictable amount before returning to normal. Tabby's star refused to follow that pattern. Sometimes, its light fell by nearly 22%, an enormous decrease for a mature star, and the events occurred at irregular intervals with no repeating schedule. The changes were too deep and too unpredictable to match the familiar signature of orbiting planets. Astronomers proposed one explanation after another. A vast swarm of comets passing in front of the star seemed possible at first, yet calculations required an implausibly large number of them. Dust drifting through space became another candidate, followed by debris from a massive planetary collision and unusual forms of activity occurring inside the star itself. Each idea accounted for certain observations, while leaving others unexplained. No single model successfully described the complete behavior recorded over years of monitoring. During that same year, astronomer Jason Wright of Pennsylvania State University published a paper discussing another possibility that quickly captured public imagination. If an advanced civilization surrounded its star with enormous structures to harvest energy, the changing arrangement of those structures might produce irregular dips in brightness. Wright did not present this as the most likely answer. He introduced it as a scientific hypothesis worthy of consideration because, at that stage, available natural explanations also struggled to match the evidence. Additional observations gradually shifted the balance. Infrared studies showed that the dimming changed with wavelength, a characteristic expected when fine dust scatters light differently across the spectrum. A solid artificial structure would not naturally produce the same effect. Those findings strengthened the case for dust while weakening the megastructure interpretation, although they still failed to identify exactly where the dust originated or why the star's behavior remained so unusual. Today, Tabby's star continues to receive careful attention from observatories around the world. Its changing brightness has not settled into a fully understood pattern, and no consensus explanation has emerged that satisfies every observation. We are left with a reminder that even a single distant star, shining from roughly 1,480 light years away, can expose the limits of familiar ideas and encourage science to keep questioning what first appears impossible. Not every planet belongs to a star. Across the Milky Way, there are worlds that travel alone, carrying no sunrise, no familiar orbit, and no parent sun to circle. Astronomers call them rogue planets, planetary mass objects moving independently through the galaxy after becoming gravitationally separated from any stellar system. They drift through interstellar space, illuminated only by distant stars that never become more than bright points against the darkness. Although they receive virtually no external warmth, these wandering worlds are not necessarily frozen solid throughout. Newly formed planets retain heat left over from their violent birth, generated as material compressed under gravity during formation. That internal energy leaks outward gradually over immense spans of time. Large rogue gas giants may therefore remain surprisingly warm deep beneath their cloud layers, long after they have lost any connection to the star that once shaped their earliest history. Current estimates suggest the Milky Way could contain more rogue planets than stars themselves. Some studies place their population at 100 billion or even higher, although the true number remains uncertain because most of these objects are extraordinarily difficult to detect. Unlike stars, they produce almost no visible light of their own. They spend their existence crossing the spaces between stellar systems, leaving only subtle clues that they are there at all. Evidence for that hidden population grew dramatically during 2023. While examining a single region within the Orion Nebula, the James Webb Space Telescope identified approximately 540 candidate rogue planets. Discovering so many possible free floating worlds in one observation field suggested these lonely objects may be far more common than astronomers once believed, especially in regions where young stars are actively forming. Some of these planets raise an especially intriguing possibility. A sufficiently massive rogue gas giant could continue generating enough internal heat to warm the interior of an icy moon orbiting around it. Beneath a thick, frozen crust, liquid water might remain stable for vast periods. Such an environment would receive no sunlight at any point in its history, relying instead upon heat from the planet itself. If microbial life requires only liquid water, chemical energy, and time, then biology might persist in places where daylight has never existed. Most rogue planets probably began their lives much differently. During the chaotic formation of planetary systems, close gravitational encounters between young worlds can become violent enough to eject one completely. Cast outward by repeated interactions, the planet escapes forever, leaving its original system behind. Countless worlds may have experienced this fate before conditions ever became suitable for life to emerge. Finding smaller rogue planets presents an even greater challenge. We usually infer their existence through gravitational microlensing, a phenomenon in which gravity briefly bends and magnifies the light from a distant background star as the unseen planet passes in front of it. The brightening lasts only a short time before disappearing, leaving behind the faint signature of a world that may spend billions of years traveling through the galaxy with no destination and no permanent home. There are moments when an entire galaxy can briefly be outshone by a single event. Among every phenomenon astronomers have observed, none releases energy more rapidly than a gamma ray burst. During only a few fleeting seconds, one of these eruptions can produce as much energy as our sun will generate across its entire 10 billion year lifetime. The explosion fades almost immediately, yet its light may continue traveling through the universe for billions of years before reaching us. Astronomers recognize two principal varieties of gamma ray burst. The shorter class lasts less than about 2 seconds and is now understood to originate primarily when two neutron stars collide after spiraling together for millions of years. The longer class continues beyond 2 seconds and forms during the catastrophic death of an exceptionally massive star. In that final collapse, the stellar core becomes a black hole while powerful jets burst outward at nearly the speed of light, piercing the dying star before escaping into space. Those jets explain why gamma ray bursts remained mysterious for decades. The radiation does not spread equally in every direction. Instead, it travels through remarkably narrow beams. We detect only the bursts whose beams happen to align with Earth. Countless others almost certainly occur beyond our view, announcing themselves to distant regions of the cosmos while passing us unnoticed. One remarkable example demonstrated just how astonishingly bright these events can become. On March 19, 2008, astronomers observed gamma ray burst 080319 Bravo. Although it originated approximately 7.5 billion light-years away, its optical afterglow briefly became bright enough to be seen with the unaided human eye under favorable conditions. No object ever viewed without a telescope had previously been observed from such an extraordinary distance. The immense power of gamma-ray bursts naturally raises another question. What would happen if one occurred much closer? Current research suggests that a burst directed toward Earth from within roughly 6,000 light-years could severely damage the ozone layer across the hemisphere facing the explosion. Increased ultraviolet radiation from the sun might then reach the surface for years afterward, disrupting ecosystems on a global scale and potentially contributing to a mass extinction. Some researchers have explored exactly that possibility while studying the late Ordovician extinction approximately 443 million years ago, when around 85% of marine species disappeared. A nearby gamma ray burst has been proposed as one possible explanation, although the evidence remains incomplete and many other hypotheses continue to be investigated. At present, no consensus identifies the true cause of that ancient biological crisis. Even with their extraordinary rarity on the scale of individual galaxies, astronomers detect roughly one gamma ray burst somewhere in the observable universe every day. Each detection marks the ending of one cosmic story while illuminating another. We witness only the few whose brilliant beams happen to cross our path, leaving the overwhelming majority to unfold beyond our line of sight, reminding us that the universe is almost certainly far more active than our limited perspective can reveal. Some mysteries emerge because our instruments disagree with one another. This one is far more unsettling. The finest telescopes and the most carefully tested methods appear to be working exactly as intended, yet they describe a universe expanding at two different rates. Both answers are supported by years of observation. Both have survived repeated scrutiny. They simply refuse to match. The quantity at the center of the puzzle is called the Hubble constant. It describes how rapidly the universe expands, measuring how quickly galaxies recede as their distance from us increases. Ever since astronomers discovered that space itself is stretching, refining this value has remained one of cosmology's central goals. Greater precision was expected to produce greater agreement. Instead, the opposite happened. One approach begins close to home. Astronomers observe Cepheid variable stars, remarkable stars whose rhythmic changes in brightness reveal their true luminosity. Once that intrinsic brightness is known, distance can be calculated with impressive accuracy. Those measurements are extended using Type Ia supernovae, stellar explosions that shine with highly consistent brightness and serve as dependable distance markers across the cosmos. Together, these observations indicate an expansion rate of roughly 73 kilometers per second for every megaparsec of distance. A completely different method starts near the beginning of cosmic history. Researchers examine the cosmic microwave background, the oldest light we can observe, and combine those measurements with the established physics of the early universe. Using that independent foundation, they calculate how rapidly expansion should proceed today. This approach consistently produces a value of approximately 67 kilometers per second for every megaparsec. The difference may appear modest at first glance. It amounts to roughly 8 or 9%. In precision cosmology, however, that gap is enormous. Independent research teams have repeated both methods using improved observations, refined statistical techniques, and different instruments. The disagreement has remained stubbornly consistent. No simple calculation error has emerged to explain it. The James Webb Space Telescope has provided one of the most significant recent tests. Its observations confirmed that the Cepheid variable star measurements are not being distorted by limitations in earlier telescope data. That result strengthened confidence in the nearby measurement instead of resolving the discrepancy. Rather than eliminating the tension, improved observations reinforced the conclusion that something deeper may be missing from our current understanding. Several possibilities remain under active investigation. Dark energy itself may evolve over time instead of remaining constant. An unknown elementary particle could have influenced conditions shortly after the Big Bang. Some researchers have even suggested that general relativity, despite its extraordinary success across more than a century of experiments, may require modification under certain cosmological conditions. None of these ideas has yet gained decisive observational support. As you follow this puzzle, the remarkable feature is not the disagreement alone. It is that nature appears internally consistent, while our best framework struggles to describe it completely. For many physicists, the Hubble tension has become one of the most important unsolved problems in modern cosmology, suggesting that the next great advance may begin with two correct answers that refuse to become one. If you could step far beyond the Milky Way and watch our galaxy from an impossible distance, you would notice something unexpected. It is not drifting aimlessly through space. Along with the neighboring galaxies that make up our local group, the Milky Way is traveling at roughly 1,400,000 miles per hour toward a particular region of the sky. That destination has become known as the Great Attractor. The direction of this motion points toward the constellations Centaurus and Hydra. Yet when astronomers attempt to study the source directly, they encounter an unusual obstacle. The view passes through the dense disk of our own galaxy, where enormous clouds of dust and countless foreground stars obscure distant objects. This hidden band is called the zone of avoidance because ordinary, visible light observations reveal remarkably little beyond it. Fortunately, visible light is only one way of exploring the universe. Radio waves and X-rays can penetrate much of the obscuring material, allowing astronomers to investigate regions that optical telescopes cannot examine clearly. Through these observations, researchers uncovered an enormous concentration of galaxies known as the Norma cluster, itself part of a vast assembly of matter extending across millions of light years. Its immense gravitational influence accounts for a significant portion of the motion observed within our cosmic neighborhood. Even so, the calculations refused to balance completely. As surveys expanded farther into space, another colossal structure entered the picture. The Shapley supercluster, located approximately 650 million light-years from Earth, contains one of the greatest concentrations of galaxies ever discovered. Its combined mass contributes substantially to the gravitational pull affecting our region of the universe. Yet after including both the Norma cluster and the Shapley supercluster, astronomers still find small discrepancies between the observed motion of galaxies and the gravity that can presently be accounted for. This does not mean an invisible object is waiting ahead like a cosmic destination. Gravity operates across immense distances, with many massive structures collectively influencing one another. The Great Attractor represents a direction of net gravitational pull rather than a single mysterious body. As observations improve, that picture continues to become more detailed, although important pieces remain uncertain. At the same time, another process unfolds across an even larger scale. Space itself continues expanding, carrying distant galaxies farther apart as the universe evolves. The Milky Way, therefore, experiences two motions simultaneously. It moves toward nearby concentrations of mass through gravity, while the broader expansion of the universe steadily increases the separation between distant galaxy groups. Perhaps the most profound lesson is not where we are headed, but what this motion reveals about our place in the cosmos. The Milky Way is neither fixed nor central. It follows gravitational influences, extending far beyond anything visible from our own perspective, participating in a continual cosmic migration shaped by structures so vast that we are still working to map them completely. There comes a point where familiar ideas about matter begin to fail. Gravity becomes so overwhelming that atoms can no longer preserve their ordinary structure, and the distinction between solid, liquid, and gas loses its meaning. The object left behind is called a neutron star, the collapsed remnant of a massive star that ended its life in a supernova explosion. Although typically only about 12 to 15 miles across, it contains between roughly 1 and 4 tenths and 2 and 1 tenths times the mass of our Sun, compressed into a sphere smaller than most cities. Inside such extraordinary conditions, matter exists in forms that cannot be recreated for more than fleeting moments in laboratories on Earth. Physicists suspect that the pressure near the core may become so immense that even neutrons themselves begin to break apart. Their constituent particles, known as quarks, may flow freely together with gluons, the particles responsible for binding quarks inside ordinary matter. This exotic state, called quark-gluon plasma, is thought to resemble conditions present only during the earliest moments after the Big Bang. Some neutron stars rotate at astonishing speeds. Hundreds of complete revolutions can occur every second, producing beams of radiation that sweep across space like the light from a distant lighthouse. Whenever one of those beams crosses Earth, our instruments record an exceptionally regular pulse. When these objects were first discovered in 1967 by Jocelyn Bell Burnell, their remarkable precision briefly led researchers to wonder whether they might represent artificial transmissions rather than natural astrophysical objects. Gravity at the surface defies ordinary intuition. A neutron star exerts roughly 200 billion times Earth's surface gravity. Imagine releasing a marshmallow from only 3 feet above the surface. Before touching the star, it would accelerate to such tremendous speed that the impact would release energy comparable to that of a nuclear explosion. Even the softest object becomes unimaginably destructive under such conditions. The crust itself endures relentless stress. Although only a relatively thin outer layer, it forms an extraordinarily rigid crystalline lattice pressed by immense gravity and powerful magnetic forces. When those stresses exceed the crust's strength, it suddenly fractures in an event known as a starquake. The resulting release of energy can rival the tremendous outbursts observed from magnetars, sending intense radiation racing across the galaxy. Neutron stars also shape the chemical history of the universe. When two of them spiral together and finally collide, they generate both gravitational waves, ripples traveling through the fabric of space and time, and an explosion called a kilonova. Within those extreme conditions, rapid nuclear reactions create many of the heaviest elements found in nature, including gold, platinum, and uranium. As you look at a piece of gold jewelry or a single grain of naturally occurring uranium, you are seeing matter forged in one of these ancient collisions. Long before the sun formed, before Earth existed, and before life emerged, neutron stars met in violent unions that scattered newly created elements across space. Every gold atom on our planet almost certainly began its journey inside one of those distant cosmic forges. Some observations become famous because they answer an important question. Others endure because they refuse to answer one at all. On August 15th, 1977, astronomer Dr. Jerry Emin was examining computer printouts from the Big Ear radio telescope at Ohio State University when he noticed an extraordinary sequence of characters. The numbers and letters represented the strength of a radio signal detected days earlier. Struck by its unusual pattern, he circled the sequence and wrote a single word in the margin. That handwritten note simply read, "Wow." The signal lasted exactly 72 seconds. That duration was not arbitrary. The Big Ear radio telescope remained fixed while Earth rotated beneath the sky, allowing any distant source to drift naturally through its observing beam. A genuine radio transmission arriving from deep space would remain visible for approximately that amount of time before passing beyond the instrument's field of view. The signal behaved exactly as such a source was expected to behave. Its characteristics became even more intriguing under closer examination. The transmission appeared near the hydrogen line, a naturally significant radio frequency produced by neutral hydrogen atoms throughout the universe. Because hydrogen is the most abundant element in space, many scientists have long suggested that an advanced civilization wishing to announce its presence might deliberately choose that frequency. The signal also possessed the intensity, narrow bandwidth, and apparent motion expected from a distant astronomical source, rather than interference produced on or around Earth. Its apparent origin pointed toward the constellation Sagittarius. Despite decades of investigation, no confirmed star, nebula, or other known natural object within that region has been identified as the source responsible for the event. More powerful radio telescopes have repeatedly observed the same area, searching for another transmission with comparable properties. Nothing matching the original detection has ever returned. Several explanations have been proposed over the years. Among the most widely discussed appeared in 2017, when researchers suggested that hydrogen clouds surrounding a pair of comets passing through the region might have generated the signal. Dr. Emin and several other astronomers questioned that interpretation, noting that it failed to reproduce important characteristics of the original observation, including its intensity and exceptionally narrow profile. The proposed explanation, therefore, never achieved broad acceptance. Today, the WOW signal occupies an unusual place in scientific history. It is neither accepted evidence of extraterrestrial intelligence nor dismissed as a solved observational error. Instead, it remains the strongest candidate for an extraterrestrial radio signal ever recorded that has not been convincingly explained through any known natural process. Perhaps the most remarkable detail is also the simplest. The signal arrived exactly as a genuine transmission from deep space was predicted to appear, persisted for precisely the expected observing interval, and then disappeared forever. Decades of increasingly sophisticated searches have expanded our knowledge of the universe in countless ways. Yet that single 72-second event continues to stand alone, inviting careful curiosity while withholding the answer that everyone hoped another observation would provide. The universe seems to follow certain rules about growth. Stars gather matter over millions of years. Galaxies assemble through repeated mergers across billions of years. Black holes are expected to grow gradually as well, feeding on surrounding gas and occasionally combining with one another. That picture works remarkably well until astronomers encounter a handful of objects so enormous that the timeline itself begins to break down. At the center of nearly every large galaxy lies a supermassive black hole. Our own Milky Way contains one known as Sagittarius A star, whose mass is approximately 4 million times greater than that of the Sunday. Although extraordinary, it fits comfortably within current theories describing how galaxies and their central black holes evolve together over cosmic history. Some black holes, however, occupy an entirely different category. One of the most astonishing is TON 618, a distant quasar located roughly 10 and 4/10 billion light-years away. Estimates place its mass near 66 billion times that of the Sunday. Its event horizon, the boundary beyond which nothing can escape, extends farther than the orbit of every planet in our solar system. It is so immense that familiar scales become almost meaningless. The difficulty is not explaining how black holes grow. We understand the basic process well. Gas falling toward a black hole forms a rapidly spinning disk that becomes intensely hot before crossing the event horizon. During that process, enormous amounts of radiation stream outward. Ironically, this brilliant emission begins limiting further growth by pushing nearby gas away, reducing the supply of fresh material available to feed the black hole. Growth eventually becomes increasingly inefficient. Yet the largest known black holes appear to have ignored that limitation. Standard models struggle to produce objects of such extraordinary mass within the available age of the universe. The challenge became even greater after the James Webb Space Telescope began observing galaxies from the universe's earliest epochs. Some existed only a few 100 million years after the Big Bang, yet they already hosted supermassive black holes far larger than conventional growth models predict should have been possible. Several ideas attempt to explain this puzzle. One proposes primordial black holes, hypothetical objects that may have formed directly from density fluctuations during the earliest moments of the universe, before the first stars ever existed. Another suggests direct collapse black holes, enormous clouds of gas that collapsed almost immediately into massive black holes without first becoming ordinary stars. Both concepts remain active areas of research, supported by intriguing theoretical work, but lacking definitive observational confirmation. A third possibility is even more profound. The earliest universe itself may have behaved differently from the picture described by today's standard cosmological model. Conditions during the first 500 million years could have allowed black holes to grow with unexpected efficiency, or through processes not yet incorporated into existing theory. As we trace these immense objects across cosmic time, they reveal more than extraordinary size. They expose a gap between observation and expectation. The black holes unquestionably exist. Their light has reached our telescopes, and their masses can be estimated with increasing confidence. The deeper question is no longer whether they formed, but how the young universe accomplished something our current understanding still struggles to explain. There is something shaping the universe that no telescope has ever seen directly. It gives off no visible light, reflects nothing, absorbs almost nothing, and has never been captured inside any detector. Even so, astronomers are convinced it exists because the universe behaves as though an enormous hidden mass surrounds every galaxy. This unseen component is called dark matter, and current measurements indicate it accounts for approximately 27% of the universe's total mass and energy content. Its presence first became apparent through gravity, when astronomers measured how rapidly stars orbit the centers of galaxies. They found a surprising result. The visible stars, gas, and dust did not provide enough mass to hold those galaxies together at the observed speeds. According to ordinary gravity, many galaxies should have gradually flown apart long ago. Instead, they remain stable, suggesting that a much larger reservoir of invisible matter supplies the missing gravitational pull. The same conclusion appears on even greater scales. Entire clusters of galaxies bend the light arriving from objects behind them through a phenomenon called gravitational lensing, the natural deflection of light by gravity. The amount of bending consistently exceeds what visible matter alone can produce. Once again, the observations point toward a substantial hidden mass that neither shines nor blocks light, yet still influences everything around it through gravity. One of the strongest pieces of evidence emerged from an object known as the bullet cluster. This remarkable system formed when two enormous galaxy clusters collided and passed through one another. The hot gas within each cluster interacted through ordinary electromagnetic forces, slowing dramatically during the encounter. The dominant source of gravity, however, continued moving, almost unaffected. Maps created from gravitational lensing showed that most of the mass had separated from the visible gas, indicating that the principal component scarcely interacts except through gravity. Few alternative explanations reproduce this behavior successfully. Physicists have proposed several candidates for dark matter: weakly interacting massive particles, hypothetical particles interacting primarily through gravity and the weak nuclear force, have been studied for decades. Axions, extremely light particles, predicted by certain extensions of particle physics, offer another possibility. Sterile neutrinos have also been suggested as potential constituents. Despite years of increasingly sophisticated experiments, none has yet been confirmed. Facilities such as the Large Underground Xenon Detector, Xenon 1T, and Panda X4T have searched for the faintest possible interactions between dark matter and ordinary matter. Located deep underground to shield them from interfering radiation, these experiments have steadily improved their sensitivity while producing no definitive detection. Each unsuccessful search narrows the possibilities without eliminating the mystery itself. Alternative theories modifying gravity have been developed to explain galactic motion without invoking dark matter. Some successfully reproduce certain observations, yet they struggle to account for systems like the bullet cluster, where the gravitational mass becomes physically separated from most of the visible matter. Whatever dark matter ultimately proves to be, or whatever unseen phenomenon produces these effects, the universe we observe could not have assembled its immense web of galaxies and clusters without it. Its invisible influence appears woven into the architecture of everything we can see. The universe offers one more surprise before we pause our journey. For much of the 20th century, astronomers expected gravity to act as a gradual brake on cosmic expansion. Every galaxy pulls on every other galaxy. Given enough time, that shared attraction seemed certain to slow the outward motion left behind by the beginning of the cosmos. Careful observations eventually revealed something far stranger. During 1998, two independent research teams studied a special class of exploding stars called Type 1a supernovae. These stellar explosions reach nearly the same intrinsic brightness, allowing astronomers to compare how bright they appear with how far away they truly are. They serve as dependable cosmic distance markers. When the measurements were complete, both teams reached the same unexpected conclusion. The expansion of the universe was not slowing, it was accelerating. The discovery transformed modern cosmology. Saul Perlmutter, Brian Schmidt, and Adam Riess were awarded the Nobel Prize in Physics during 2011 for demonstrating this remarkable behavior. Yet the prize recognized an observation rather than an explanation. Something throughout the universe appears to be overcoming gravity across the greatest distances we can measure, and its true nature remains one of the deepest mysteries in science. Astronomers call this unknown influence dark energy. The name describes what it does rather than what it is. It may be a property woven into space itself. It could arise from an undiscovered field filling the cosmos. It may even point toward physics that has not yet been imagined. Current observations indicate that dark energy represents approximately 68% of the universe's total energy content, making everything visible, from stars to planets to galaxies, only a small fraction of the cosmic whole. Decades before anyone recognized its significance, Albert Einstein introduced a mathematical term known as the cosmological constant, while developing general relativity. Later, he reportedly regarded that addition as his greatest blunder after evidence suggested the universe was expanding. Remarkably, the same mathematical idea now provides the closest description of how dark energy behaves across the observable universe, although whether it truly represents the underlying cause remains uncertain. One consequence seems almost impossible at first hearing. Extremely distant galaxies can recede from us faster than light without violating relativity because they are not racing through space faster than light travels. Instead, space itself is stretching between us and them. As that fabric expands, the distance grows even though neither galaxy locally exceeds the universal speed limit. If dark energy continues acting with its present strength, an unimaginably distant future awaits. Nearly every galaxy beyond our local group will disappear beyond the observable horizon, leaving the Milky Way and its nearby companions alone beneath the sky. Some theoretical models go further. They propose a scenario called the Big Rip, in which dark energy steadily grows stronger until galaxies, stars, planets, molecules, and ultimately even atoms can no longer remain bound together. Whether that fate awaits the cosmos is unknown, but the possibility reminds us that the largest force shaping the universe may also be the least understood. Long before our own galaxy settled into its present rhythm, certain galaxies blazed with an intensity that seems almost impossible today. Their combined starlight was overwhelmed by a single region at the center. Across billions of light years, these brilliant beacons announced themselves before the galaxies surrounding them could even be clearly distinguished. We know them as quasars, among the most luminous objects ever observed. A quasar is an active galactic nucleus, the energetic heart of a galaxy where a supermassive black hole is consuming enormous amounts of surrounding matter. Gas and dust do not plunge directly inward. They first spiral into a rapidly rotating disk, where friction compresses and heats the material until it shines with extraordinary power across the electromagnetic spectrum. The light comes from the infalling matter, not from the black hole itself, whose interior remains hidden beyond the event horizon. The scale quickly escapes ordinary comparison. During 2024, astronomers confirmed the brightest known quasar, J0529-4 351. Its brilliance is estimated at roughly 500 trillion times greater than that of our Sun, equivalent to approximately 2 trillion suns radiating at once. To sustain such astonishing output, the central black hole consumes about one solar mass of material every single day. Even on cosmic timescales, that feeding rate is remarkable. Looking outward also means looking backward through time. Most quasars are found in the distant universe, their light beginning its journey when galaxies were still assembling their earliest large structures. You are seeing an era when collisions were common, reservoirs of gas were plentiful, and supermassive black holes grew with astonishing speed. The youthful universe was a far more turbulent place than the one surrounding the Milky Way today. Many quasars unleash narrow jets of charged particles, traveling at speeds approaching that of light. Guided by powerful magnetic fields, these streams can extend for hundreds of thousands of light years beyond their host galaxies. They inject tremendous amounts of energy into surrounding gas, preventing that gas from cooling and collapsing into new stars. In this way, a feeding black hole can influence the evolution of an entire galaxy, shaping generations of stars that may never form. Our own galactic center tells a calmer story today. Sagittarius A star currently feeds only sparingly, producing nothing like the overwhelming radiance of a quasar. Evidence suggests, however, that billions of years ago, The Milky Way almost certainly passed through an active quasar phase. The peaceful galaxy you know now was once dominated by the same fierce processes observed across the distant universe. Perhaps the most striking image remains the simplest. Billions of stars together can vanish beneath the glare of one feeding black hole. Entire galaxies become little more than a faint backdrop, while a single cosmic engine commands the view, reminding us that gravity, under the right conditions, can create some of the brightest lights the universe has ever known. Every direction you can face carries the same invisible boundary. It does not mark the end of existence. Instead, it marks the limit of what the universe has been able to reveal to us since its beginning. Beyond that horizon, the cosmos continues, but its light has not had enough time to arrive. We travel now to the greatest distance observation allows, where knowledge gradually gives way to possibility. The observable universe spans approximately 93 billion light years in diameter. That astonishing scale is determined by time rather than by a physical wall. Since the beginning of cosmic expansion, light has traveled across an evolving universe, carrying information from distant galaxies toward us. Anything beyond this horizon remains forever outside our view, not because it does not exist, but because its light cannot reach us under the present conditions of cosmic expansion. Current evidence suggests the universe itself extends much farther than the observable portion. It may stretch so far that no meaningful edge exists at all. Some cosmological models even allow for an infinite universe. If that is true, then every physically possible arrangement of stars, planets, and galaxies would eventually occur somewhere. Statistical necessity would imply regions indistinguishable from our own solar system, and even worlds identical to Earth, separated by distances so immense that no message could ever bridge them. The farthest confirmed galaxy candidate presently observed, known as Hotel Delta 1, appears approximately 13.5 billion light-years away. You are seeing it as it existed when the universe was only about 300 million years old. Across that tremendous gulf, its ancient light has traveled almost the entire history of cosmic time before finally reaching our telescopes. There is, however, a deeper boundary still. Before roughly 380,000 years had passed after the beginning of the universe, space was filled with an intensely hot plasma, a state of matter where electrons and atomic nuclei moved independently instead of forming atoms. Light scattered constantly through this glowing fog and could not travel freely. The cosmic microwave background is the oldest electromagnetic light that escaped once atoms finally formed and the universe became transparent. No telescope observing electromagnetic radiation can look beyond that moment. Our horizon is not fixed forever. As dark energy continues driving cosmic expansion, more distant galaxies will eventually cross beyond the observable limit. Their final light will arrive, fade, and never be replaced. Future civilizations, living trillions of years from now, may inherit a sky containing far fewer galaxies than we can see today. In that sense, the observable universe is more than a map of distance. It is a temporary window. We exist inside a vast sphere defined by the speed of light and the age of the cosmos, and with every passing age, that window narrows a little more, preserving some chapters of cosmic history while placing countless others forever beyond observation. Galaxies may appear permanent when viewed across a human lifetime, yet they are constantly changing through encounters with their neighbors. Far from being rare accidents, these immense interactions are among the primary forces shaping the appearance of the universe. Even the Milky Way is participating in this long process today, steadily gathering smaller companions into its own expanding structure. One of those companions is the Sagittarius dwarf galaxy. For billions of years, it has followed an elongated path around the Milky Way, returning again and again under the influence of our galaxy's gravity. Each close passage tears away more of its stars. Those stars do not simply disappear. They spread into vast stellar streams that wrap around the Milky Way like enormous ribbons, gradually blending into the larger galaxy. Some of the stars, now passing through our own galactic disk, almost certainly began their existence inside this much smaller system. Another neighboring galaxy, the Large Magellanic Cloud, remains intact for now. Visible from the southern hemisphere as a faint, glowing cloud, it continues its journey around the Milky Way, while gravity slowly alters its course. Current models indicate that approximately 2 and 4 tenths billion years from now, it will collide with our galaxy. The event will reshape both systems, stirring gas clouds, triggering waves of new star formation, and changing the overall structure of the Milky Way long before an even greater encounter begins. That larger meeting will arrive roughly 4.5 billion years from now, when the Milky Way and the Andromeda Galaxy begin merging into a single system. Rather than a brief impact, the process will unfold across hundreds of millions of years. Their spiral arms will stretch, twist, and intertwine under immense gravitational forces. Vast clouds of gas will compress into brilliant nurseries where countless new stars ignite, while the original shapes of both galaxies gradually disappear. The scale of this collision can sound alarming until you consider the enormous distances separating individual stars. Although two giant galaxies will pass directly through one another, the chance of any single star striking another is extraordinarily small. Most stars will continue their journeys undisturbed, guided only by changing gravitational paths. Our own sun will likely survive, although it may find itself orbiting within an entirely different region of the newly formed galaxy. Astronomers have already given this future creation a name, Milkomeda. It represents the combined legacy of two great spiral galaxies becoming one larger system. If Earth still existed during the earliest stages of that merger, Andromeda would no longer resemble a distant smudge. Its magnificent spiral arms would stretch across the entire sky, filling the heavens with a view unlike anything witnessed during human history. The spectacle would unfold with breathtaking grandeur, yet every indication suggests there will be no human eyes remaining to watch as our galaxy slowly becomes something entirely new. A single question has echoed through modern astronomy for generations, and it was first spoken during an ordinary lunch. In 1950, physicist Enrico Fermi listened to a discussion about extraterrestrial life before asking a remarkably simple question: where is everybody? You can almost hear how ordinary those words sounded. Their meaning, however, reaches across the entire observable universe. The puzzle is straightforward. Our galaxy contains hundreds of billions of stars, many with planets. Countless stars are billions of years older than our own sun, giving any civilization around them immense stretches of time to develop technology, spread between neighboring systems, or leave unmistakable traces behind. Even at modest speeds, a determined civilization could cross the Milky Way in a tiny fraction of the galaxy's lifetime. Yet every careful search has reached the same destination. We have found no confirmed evidence that anyone else is calling across the darkness. To explore this mystery, astronomer Frank Drake introduced the Drake equation in 1961. Rather than producing a single answer, the equation combines several unknown factors, including how often stars form planets, how frequently life begins, And how many civilizations develop technology capable of communication? Depending on the values assigned to those unknowns, the result ranges from almost no communicating civilizations to millions scattered throughout the galaxy. The equation does not solve the mystery. Instead, it reveals how much remains uncertain. This uncertainty leads directly to the deepest tension in the paradox. If technological civilizations commonly emerge, why is the sky so empty of unmistakable signals, artificial structures, or enduring artifacts? Radio telescopes continue listening, observatories continue searching. The expected chorus has never clearly appeared. One proposed explanation is known as the Great Filter. The term describes an unknown barrier so difficult that almost nothing passes beyond it. Perhaps the hardest step was the origin of life itself, making living worlds extraordinarily uncommon. It is equally possible that simple organisms appear often, while the transition to complex cells, multicellular creatures, or enduring technological societies almost always fails. Which possibility would you rather be true? That question becomes more unsettling if the filter has not yet been crossed by our own civilization. In that case, many intelligent species may have reached remarkable achievements before encountering an obstacle none could overcome. Their absence would not represent emptiness. It would represent unfinished stories scattered across cosmic history. Since 1960, the search for extraterrestrial intelligence has systematically listened for signals that stand apart from nature. Decades have passed without a confirmed detection. That continuing absence does not prove humanity is alone. It steadily narrows the possibilities, reminding us that every new observation refines the mystery instead of dissolving it. As we continue listening together, the universe answers with the same enduring response, an immense expanse that has not yet revealed whether anyone else is listening too. Long before any instrument could respond, the universe had already begun another conversation. This one does not travel as light, radio waves, or particles. Instead, it moves through the fabric of space and time itself, stretching and compressing distance as it passes. For nearly a century, this remarkable prediction remained one of Albert Einstein's boldest ideas, existing only within mathematics until human technology finally became sensitive enough to hear its faint arrival. That moment came on September 14th, 2015. At the Laser Interferometer Gravitational Wave Observatory, researchers recorded a signal later named gravitational wave 150914. Two black holes had completed a slow spiral around one another, approximately 1.3 billion light-years away, before merging into a single, larger black hole. The collision did not simply release light. It disturbed space and time themselves, sending ripples outward in every direction across the cosmos. When those ripples finally reached Earth, they passed directly through our planet without slowing or scattering. The observatory measured a change so unbelievably small that its mirrors shifted by less than 1,000th the diameter of a proton. Yet, within that almost unimaginable precision lay unmistakable evidence that space itself had briefly changed shape around us. During the final instant before the merger settled, energy equal to approximately 3 times the mass of our Sun was transformed entirely into gravitational wave energy. Nothing blocked those waves during their immense journey. Gas, stars, galaxies, and entire clusters offered no meaningful resistance. Unlike light, gravitational waves cannot be absorbed, reflected, or hidden by intervening matter. They carry information from places that electromagnetic radiation alone cannot fully reveal. Another milestone followed in 2017. Astronomers observed two neutron stars colliding, producing both gravitational waves and visible light from the same event. This became the first successful example of multi-messenger astronomy, meaning scientists studied one cosmic event through two completely different forms of information. The nearly simultaneous arrival of both signals also confirmed that gravitational waves travel at the speed of light, strengthening one of the central predictions of general relativity. Today, our ability to listen continues expanding. Networks known as pulsar timing arrays use rapidly rotating neutron stars as extraordinarily precise cosmic clocks. By measuring tiny changes in the arrival times of their pulses, astronomers have detected a broad background hum of gravitational waves filling the universe. The most likely source is countless pairs of supermassive black holes orbiting one another over millions of years before they eventually merge. As you look upward, nothing in the sky reveals this continuous symphony, yet it has surrounded every generation that ever lived. These ripples have crossed the cosmos since the earliest moments after the Big Bang, carrying a record written directly into space and time itself. Only now have we begun to understand that the universe has always been speaking in more than light. Every star you have ever seen is living through a story so vast that entire civilizations could rise and disappear before a single chapter concludes. We measure our lives in decades, yet stars spend billions of years transforming the simplest element in the universe into the heavier ingredients that eventually become planets, oceans, and living worlds. Even now, countless stars are approaching endings unlike anything we experience on Earth. Our own sun is approximately 4.6 billion years old. It has enough hydrogen remaining to continue shining for roughly another 5 billion years. Eventually, that fuel will become exhausted. The core will contract while the outer layers swell outward, transforming the sun into a red giant. Mercury will disappear first. Venus will follow. Earth may also be engulfed, although its exact fate remains uncertain as the expanding atmosphere reaches across the inner solar system. That giant star will not endure. After shedding its outer layers into space, the remaining core will become a planetary nebula, a glowing shell of gas surrounding an exposed stellar remnant. At the center will remain a white dwarf, a sphere approximately the size of Earth, containing nearly the entire original mass of the Sunday fusion, will have ended forever. From that point onward, it will simply radiate away its stored heat across unimaginable ages. More massive stars follow a far more dramatic path. Once a star containing roughly 8 or more solar masses exhausts its nuclear fuel, gravity overwhelms the core in less than a second. The collapse triggers a core collapse supernova, blasting the outer layers into surrounding space, while the crushed center becomes either a neutron star or, if enough mass remains, a black hole. Those explosions scatter newly forged elements across galaxies, providing the raw material from which future stars and planets eventually emerge. Yet some of the largest stars may avoid even that spectacular farewell. Evidence suggests certain giants collapse directly into black holes without producing a brilliant explosion. One compelling example is the star known as November 6, 946, Black Hole 1. Roughly 25 times the mass of our Sun, it gradually faded before disappearing during 2009. No bright supernova followed. A star that once illuminated its galaxy simply vanished from view. You can even find another future ending with your own eyes. Betelgeuse, the enormous red supergiant marking Orion's shoulder, has entered the closing stages of its life. Sometime within approximately 100,000 years, it is expected to explode as a supernova, bright enough to remain visible even during daylight. White dwarfs also hold one final possibility. In binary systems, where two stars orbit one another, a white dwarf can slowly gather matter from its companion. If it exceeds 1.4 solar masses, a boundary known as the Chandrasekhar limit, it detonates as a type Ia supernova. These remarkably consistent explosions became the cosmic measuring tools that revealed the accelerating expansion of the universe. Yet the final chapter has still never arrived. No black dwarf exists today because the universe itself has not existed long enough for even the oldest white dwarf to cool into that ultimate dark remnant. If you could step far enough away from every galaxy, every cluster, and every familiar landmark in the cosmos, an unexpected pattern would begin to emerge. The universe is not arranged like scattered grains of sand. Instead, matter gathers into an immense framework of connected strands, dense intersections, and astonishingly empty regions. Astronomers call this arrangement the cosmic web, the largest known pattern ever identified in nature. This structure stretches across the observable universe. Individual filaments extend for hundreds of millions of light years, linking galaxy clusters into an intricate network that continues beyond every horizon we can presently explore. Between those luminous strands lie enormous voids where comparatively few galaxies reside. Rather than filling space evenly, matter has spent billions of years flowing into these interconnected pathways under the influence of gravity. Long before telescopes revealed this architecture, computer simulations predicted it should exist. Those simulations assumed that dark matter, though invisible, provided the dominant gravitational framework shaping the young universe. Ordinary matter gradually followed that hidden scaffold, collecting where gravity was strongest until galaxies and clusters emerged along the filaments. Later observations closely matched those predictions, providing one of the strongest confirmations that dark matter correctly describes the formation of large-scale cosmic structure. As we examine the intersections of these vast strands, we discover the busiest neighborhoods in the universe. Galaxy clusters gather where multiple filaments meet, creating immense concentrations of matter. In contrast, regions such as the Boötes Void occupy the spaces between those strands. These immense expanses contain remarkably few galaxies, emphasizing how unevenly matter is distributed across the largest observable distances. Some discoveries continue to test our understanding. One of the most remarkable is the Hercules Corona Borealis Great Wall, identified in 2013. Spanning approximately 10 billion light-years, it is presently regarded as the largest known structure within the observable universe. Its extraordinary scale challenges the long-held cosmological assumption that the universe becomes broadly uniform when viewed across sufficiently large distances. Instead, it hints that the largest patterns may be even more complex than expected. More recently, researchers announced another surprise. During 2024, astronomers identified a structure known as the Big Ring. Measuring approximately 1.3 billion light-years in diameter, its nearly circular geometry does not fit comfortably within current cosmological models. Whether it represents an unusual statistical fluctuation or evidence of missing physics remains uncertain. Even now, this immense network continues evolving. Dark matter keeps drawing material into denser filaments, while the expansion of space simultaneously carries distant regions farther apart. Those two processes unfold together, shaping the largest architecture we have ever mapped. As you picture our own Milky Way within that immeasurable framework, it becomes only one luminous point, resting upon a strand of a structure so vast that humanity has only recently begun to perceive its full design. There was a time when the universe contained no stars at all. No galaxies traced graceful spirals across space. No planets circled distant suns. Even the faintest point of starlight had not yet appeared. After the earliest moments of cosmic expansion, the universe remained filled with intense heat until, approximately 380,000 years later, it cooled enough for electrons to join with protons, creating the first hydrogen atoms. For the first time, light could travel freely across space. Yet there was almost nothing to illuminate. Cosmologists call this era the cosmic dark ages. Across hundreds of millions of years, immense clouds of hydrogen and helium drifted through an expanding universe without a single star to brighten them. Gravity worked patiently throughout that immense span, drawing slightly denser regions together until the first pockets of gas became heavy enough to collapse under their own weight. From those collapsing clouds emerged the first generation of stars, known as population, three stars. They began forming approximately 100 million to 250 million years after the Big Bang. Unlike every familiar star we see today, these pioneers contained almost nothing except hydrogen and helium. Heavier elements had not yet been created anywhere in the universe. The raw ingredients for rocky planets, oceans, and living organisms simply did not exist. Theory suggests these first stars were extraordinary. Many may have possessed hundreds of times the mass of our Sunday. Such enormous stars consumed their fuel with astonishing speed, shining brilliantly before ending their lives after only a few million years. Their brief existence transformed the chemistry of the cosmos forever. When these giants exploded as supernovae, they forged the universe's first heavy elements. Carbon appeared for the first time. Oxygen followed. Nitrogen and iron joined the expanding clouds of stellar debris. Those freshly created atoms mixed into surrounding gas, becoming the building blocks from which later generations of stars and planets eventually formed. Every rocky world, every atmosphere, and every living cell traces its origins back to those ancient explosions. Finding direct evidence of population 3 stars has remained one of astronomy's greatest challenges because they vanished so early in cosmic history. But the James Webb Space Telescope has begun detecting light from extremely distant young galaxies with signatures that may be consistent with these primordial stars. Although confirmation continues to require careful study, these observations offer our strongest glimpse yet into the universe's first stellar generation. As you consider your own place within this story, an extraordinary connection emerges. Every atom in your body, heavier than hydrogen, was forged inside a star. The oldest of those atoms were created by stellar ancestors that lived and died before the sun existed, before Earth formed, and before the Milky Way had assembled into the galaxy we recognize today. Long before any world could support life, those forgotten stars had already begun writing the chemical story that eventually became you. Long before the first planet beyond our solar system was confirmed, we imagined other worlds by borrowing familiar ideas from our own. We expected rocky planets resembling Earth, giant worlds resembling Jupiter, and perhaps a few modest variations between them. As discoveries accumulated, that comfortable picture dissolved. With more than 5,700 confirmed exoplanets identified by the year 2024, the universe revealed a creativity far beyond those early expectations. Some of these distant worlds seem almost impossible at first glance. 55 Cancri e, orbiting approximately 41 light-years from Earth, circles so close to its parent star that its surface is believed to be covered by a global ocean of molten lava. Temperatures climb to roughly 3,600 degrees Fahrenheit. Under such extreme conditions, rock itself can vaporize, creating an atmosphere unlike anything found within our own planetary neighborhood. Another remarkable example is WASP 76b, a giant planet orbiting so near its star that its dayside reaches temperatures exceeding 4,350 degrees Fahrenheit. Iron cannot remain solid there. Instead, it becomes vapor high within the atmosphere. As powerful winds carry that material toward the cooler hemisphere, the iron condenses into molten droplets before falling once again. We often imagine rain as water, yet this distant world reshapes that familiar idea into something astonishing. Far away, another giant called Hotel Delta 189733b appears deep blue when viewed from space. The color suggests serenity, yet the reality is anything but gentle. Tiny silicate particles, the same basic material found in glass, are carried through the atmosphere by winds approaching 5,000 miles per hour. Those particles become a relentless, sideways storm of microscopic glass fragments driven across the planet without pause. Not every extraordinary world is defined by extreme weather. Kepler 1, 6b circles two stars instead of one, confirming that planetary systems once considered suitable only for science fiction can remain stable over immense spans of time. Although this gas giant cannot support life as we know it, its orbit demonstrated that nature allows far more diverse planetary arrangements than astronomers once believed. The TRAPPIST-1 system expands that lesson even further. 7 Earth-sized planets orbit a cool red dwarf star, with 3 traveling through the region where temperatures could allow liquid water under suitable atmospheric conditions. The James Webb Space Telescope is now examining those atmospheres, searching for the chemical fingerprints that may reveal how these worlds have evolved. As we continue this journey, each newly discovered planet reminds you that our own solar system represents only one outcome among countless possibilities. The remarkable diversity of exoplanets suggests the universe conducts an immense experiment in planetary physics, producing environments more varied than any single imagination could invent. We have explored only a tiny fraction of those distant worlds, and already they have transformed our understanding of what a planet can become. Imagine the earliest moments after the Big Bang, when the newborn universe contained unimaginable energy and every physical process unfolded with remarkable balance. According to our best understanding of particle physics, each newly created particle of matter should have been accompanied by a matching particle of antimatter. Antimatter mirrors ordinary matter in nearly every way, sharing the same mass while carrying the opposite electric charge. Whenever the two meet, they annihilate one another, releasing their mass as pure energy. If that balance had remained perfect, the outcome would have been astonishingly simple. Every particle would have found its opposite. Matter and antimatter would have disappeared together, leaving behind a universe filled only with radiation expanding into darkness. No atoms would have assembled, no stars would have ignited, no galaxies, planets, oceans, or living beings would ever have emerged. As you follow this story, your own existence points toward a profound conclusion. Something interrupted that perfect symmetry. The difference was extraordinarily small. For roughly every billion pairs of matter and antimatter particles that destroyed one another, only a single extra particle of matter remained behind. That tiny surplus survived the universal annihilation. Across billions of years, Those surviving particles became hydrogen clouds, blazing stars, heavy elements, rocky worlds, and eventually every living organism we know. Every object you can see traces its history to that almost imperceptible imbalance. Physicists call this mystery baryon asymmetry, a term describing the unexpected excess of ordinary matter over antimatter throughout the observable universe. One possible clue comes from a phenomenon known as charge parity violation. Charge parity refers to a mathematical symmetry that compares matter with antimatter while also reversing spatial coordinates, almost as though nature were viewed in a perfect mirror. Experiments have confirmed that this symmetry can be violated under specific conditions. Matter and antimatter do not always behave as exact reflections of one another. That discovery represented an important breakthrough, yet it did not solve the larger puzzle. The Standard Model of Particle Physics, our most successful framework for describing fundamental particles and their interactions, predicts a small amount of charge parity violation. Unfortunately, the predicted imbalance falls dramatically short of what the observable universe requires. The mathematics allows a slight preference for matter, but nowhere near enough to explain why entire galaxies exist instead of empty radiation. But the question remains remarkably direct. Why did nature choose matter over antimatter by such a tiny margin? Every telescope, every spacecraft, every distant galaxy, and every person asking that question depends upon an answer we have not yet found. Somewhere within the earliest history of the cosmos, a process unfolded that tipped the balance by the smallest imaginable amount. Without it, there would have been no enduring matter to shape the universe we continue exploring together. Few discoveries have transformed our understanding of black holes more profoundly than a realization reached during the 1970s. Until then, black holes were thought to be perfect cosmic prisons, swallowing everything while returning nothing. In 1974, Stephen Hawking demonstrated through mathematics that quantum effects near the event horizon, the boundary beyond which nothing can escape, change that picture completely. Black holes are not entirely black. They emit an extremely faint glow, now known as Hawking radiation. The process is unimaginably slow. A black hole with the mass of a star would survive for a span of time vastly exceeding the present age of the universe. Yet, the conclusion remains remarkable. Given enough time, every black hole should gradually lose energy, shrink, and eventually disappear altogether. What once seemed permanent is instead temporary, unfolding across intervals so immense that ordinary language struggles to describe them. That discovery opened a much deeper mystery. Every particle falling into a black hole carries information about its exact quantum state, meaning the complete microscopic description of its physical properties. Quantum mechanics, our most successful theory describing matter at the smallest scales, insists that such information cannot truly vanish from reality. Even if particles change form, the underlying information must remain recoverable in principle. General relativity appears to tell a different story. If a black hole eventually evaporates into featureless Hawking radiation, the detailed information about everything it consumed seems to disappear forever. Once the black hole is gone, nothing appears to preserve the unique history of the matter that entered it. We are left confronting two extraordinarily successful theories, making incompatible claims about one of nature's most fundamental rules. The tension became even sharper in 2012 with the proposal known as the firewall paradox. Several physicists argued that preserving quantum information might require the event horizon to become an intensely energetic barrier. Instead of crossing that boundary without noticing anything unusual, as general relativity predicts, An infalling traveler would encounter devastating radiation at the threshold itself. The proposal protects one principle while undermining another, revealing how difficult this puzzle has become. Many possible solutions remain under active investigation. Some researchers suggest the missing information is subtly encoded within Hawking radiation, even though it appears completely random. Others propose that information is stored across the event horizon through a holographic description, meaning the surface contains a complete record of everything that entered. Another possibility is even more profound. A future theory of quantum gravity, uniting quantum mechanics with general relativity, may reveal principles that current mathematics cannot yet express. As we follow this trail, the paradox refuses to fade into abstraction. It reaches the foundation of modern physics itself. Can the universe truly erase information, or have we misunderstood the deepest laws governing space, time, and reality? Until those questions find a common answer, one of the greatest achievements in theoretical physics remains incomplete, inviting us to look beyond today's understanding toward an even more fundamental description of the cosmos. There is a direction hidden within the history of the universe. Galaxies drift, stars ignite, black holes grow, and atoms rearrange themselves according to countless local events. Beneath every one of those changes lies a deeper principle known as the second law of thermodynamics. Entropy, a measure of how evenly energy becomes distributed within a closed system, increases over time. Applied to the universe as a whole, it points toward a future unlike any era that came before. This long evolution leads toward thermodynamic equilibrium, more commonly called the heat death of the universe. Despite its dramatic name, it does not describe an explosion or a sudden ending. Instead, it marks the gradual disappearance of every useful energy difference capable of driving physical processes. Stars, galaxies, and even black holes are temporary chapters in that immense progression. The first major transition arrives after approximately 100 trillion years. By then, nearly all of the gas required to create new stars will have been consumed or locked away. Star formation will come to an end. Existing stars will continue their own life cycles, but the universe will no longer replenish its supply of fresh stellar light. Each generation will leave behind remnants without successors to replace them. Far beyond that unimaginable era, another possibility emerges. If protons are ultimately unstable, something experiments have not yet confirmed, they may decay after approximately 10 to the 40th years. Ordinary matter itself would gradually dissolve. Even objects that appear permanent today would slowly disappear across intervals so vast that comparison becomes meaningless. The universe would continue changing, although at a pace almost impossible to imagine. Black holes endure far longer than stars. Through Hawking radiation, they lose energy with extraordinary slowness. Stellar mass black holes are expected to finish evaporating after roughly 10 to the 67th years. The largest supermassive black holes persist longer still, surviving until approximately 10 to the 100th years before releasing their final traces of energy into space. Even these seemingly eternal objects eventually reach an ending. Beyond that point, the cosmos settles into its final condition. Matter becomes extraordinarily sparse. Only widely separated photons, neutrinos, electrons, and perhaps a few remaining elementary particles drift across an expanding universe. Temperature differences disappear. Energy no longer flows from one region to another. Without those gradients, no new structures can emerge because every physical process requires an imbalance to accomplish work. As we consider that distant future, the conclusion is neither catastrophic nor immediate. The timescales extend so far beyond human history that they resist ordinary comprehension. Yet the underlying direction remains fixed. Every star shining above you tonight is consuming a limited reserve of fuel. The universe is not standing still. Across incomprehensible ages, it is steadily moving toward a future where change itself becomes vanishingly rare. Across this journey, a pattern has slowly emerged. Dark matter refuses to reveal its identity. Dark energy drives cosmic expansion without exposing its source. Vast radio bursts appear and vanish with extraordinary power. The Hubble tension challenges our measurements of the universe itself. The wow signal remains unexplained after decades of careful examination. The black hole information paradox continues to place two foundational theories into direct conflict. None of these mysteries survives because scientists have ignored them. They endure because every careful investigation has uncovered new questions instead of final answers. Together, dark matter and dark energy account for approximately 95% of the universe. Yet the standard model of particle physics, the most successful predictive framework ever developed for the behavior of fundamental particles, offers no explanation for either one. The theory has passed countless experimental tests with extraordinary precision. At the same time, it leaves most of the universe beyond its descriptive reach. That contrast is one of the defining realities of modern science. The remarkable instruments built to explore these mysteries have not reduced their significance. Quite the opposite. The James Webb Space Telescope peers farther into cosmic history than any previous observatory. Gravitational wave detectors measure distortions smaller than a proton. Particle accelerators recreate conditions approaching those of the early universe. Radio telescopes scan immense regions of the sky with astonishing sensitivity. Each technological advance sharpens our view, yet the deeper picture grows more intricate rather than simpler. History suggests that this outcome should not surprise us. During the late 19th century, many physicists believed they were approaching a nearly complete understanding of nature. Classical mechanics appeared capable of explaining almost everything that mattered. Within only a few decades, quantum mechanics and general relativity transformed that confidence into something far more humble. The deepest assumptions of one generation became the starting point for another. Today we stand in a similarly uncertain position. The origin of matter over antimatter, the true nature of dark matter, the cause of dark energy, and a successful theory of quantum gravity remain unresolved despite immense intellectual effort. It is entirely possible that answering these questions will require concepts beyond the mathematical language available today. Future discoveries may reshape our understanding as profoundly as relativity reshaped the universe, known to Einstein's predecessors. As we reach this point together, the enduring mysteries are not signs that science has failed. They demonstrate that the universe continues to exceed the boundaries of our current understanding. Human minds evolved on a small planet, orbiting an ordinary star within one galaxy among countless others. From that modest beginning, you and I have traced evidence across billions of light years and billions of years of cosmic history. The farther we have learned to see, the more clearly the universe has revealed that its greatest discoveries still lie beyond the horizon of what we presently know. There is another perspective that emerges only after stepping back from every discovery we have explored together. It is not centered on any single galaxy, particle, or equation. Instead, it asks where, in the immense lifetime of the universe, you and I happen to exist. The answer is remarkably specific. The universe is approximately 13,800,000,000 years old, yet its future may extend beyond one Google years, a number written as 1 followed by 100 zeros. Between those unimaginable boundaries lies the stelliferous era, the age of stars. This is the chapter of cosmic history when hydrogen continues to ignite inside stellar cores, filling galaxies with light, forging heavier elements, and providing the steady energy that allows planets and living systems to emerge. It is only one chapter. It will eventually come to an end. Even within this era, we have arrived after its greatest burst of creation. Star formation reached its peak roughly 10 billion years ago when galaxies transformed immense reservoirs of gas into brilliant new suns at far higher rates than we observe today. Those reserves have steadily diminished. Across the observable universe, fewer stars are being born now than during those earlier epochs. The cosmos still shines magnificently, but its most productive age already belongs to the distant past. Our timing is remarkable for another reason. We live during the first moments in Earth's history when a technological civilization can detect gravitational waves, observe the cosmic microwave background, discover thousands of planets beyond our own solar system, and measure the accelerating expansion of the universe. Only 2 centuries ago, none of these realities had entered human knowledge. The sky above was the same, yet the universe it contained was profoundly smaller in our understanding. Meanwhile, the observable universe continues to change around us. Because space itself expands, distant galaxies gradually recede beyond the cosmic horizon. Their ancient light still reaches us today, but future observers, living trillions of years from now, may never know those galaxies existed at all. Entire regions, presently visible, will fade beyond any possible observation, carrying their histories permanently out of reach. Seen together, these facts reveal an extraordinary intersection of circumstance. We inhabit an era when stars still illuminate the heavens, when the oldest light remains detectable, when neighboring galaxies can still be studied, and when the laws of physics have become understandable enough to uncover questions far deeper than anyone once imagined. This combination has existed only briefly and will never appear in exactly the same form again. As you look upward tonight, every visible galaxy, every measurable signal, and every insight gathered by generations of curious minds belongs to this singular moment in cosmic history. The universe has offered us a brief opportunity to witness it, while so much remains visible, and while so many of its greatest mysteries are still waiting to be understood. We arrive here carrying every mystery that has accompanied us across this journey: the unexplained signal, the immense cosmic void, the expanding universe that refuses to fit perfectly within our equations, the distant magnetar whose outburst reached across 50,000 light-years and briefly disturbed Earth's ionosphere. Together they form something larger than a collection of astonishing discoveries. They mark the present boundary of human understanding. What unsettles the imagination is not the violence of the cosmos. Exploding stars, colliding galaxies, and black holes have become familiar features of the universe we have explored together. The deeper realization is that nature continues to produce measurable phenomena that remain beyond the explanatory reach of our finest theories. Our most advanced observatories have not erased these mysteries. They have confirmed them with increasing precision. Consider how improbable our perspective truly is. We are a species that evolved on a small world orbiting an ordinary star, located within one spiral arm of a galaxy that is itself only one among roughly 2 trillion galaxies across the observable universe. Yet within little more than 100 years, we have detected the oldest light still traveling through space, mapped enormous structures spanning billions of light years, discovered thousands of distant planets, and measured ripples in space and time created by black holes merging more than 1 billion light years away. Each achievement has expanded our knowledge. Each has also revealed another horizon beyond it. That pattern has repeated throughout the history of science. Every generation has believed the remaining questions were becoming fewer. Every generation eventually discovered entirely new landscapes of uncertainty waiting beyond the previous frontier. The unknown, then, is not evidence that the search has failed. It is evidence that the search is genuine. Whenever observations refuse to match expectation, the universe is revealing that something real exists beyond our current explanations. Those discrepancies are not empty spaces in knowledge. They are signposts pointing toward discoveries that have not yet found their mathematics. As you look into the night sky, it may appear calm and familiar, yet every direction contains messages still being decoded. Invisible forms of matter continue shaping galaxies. The expansion of space still accelerates for reasons we cannot fully explain. Countless signals cross the cosmos, whether or not we presently understand their origin. The universe is filled with evidence, waiting patiently for minds capable of recognizing what it has been saying all along. Perhaps that is the most remarkable conclusion we can reach. The cosmos is not withholding its secrets. It leaves traces, patterns, and laws wherever we learn to look. Our understanding grows because those laws remain consistent, even when they surprise us. We are made of the wreckage of dead stars, asking why the universe exists, and somehow that is the least disturbing thing we found.